In the last video, we saw how the equation continuity will dictate changes in the speed of a fluid given the changes in dimensions of the pipes. Now finally, we will go and take a look at what happens if we change height in our fluid. So in this example here, we've got a skinny pipe that's going to start going uphill and into a fatter pipe. By continuity, since this is a skinny pipe, the fluid here has to be going faster than the fluid here. However, we also realize that if I follow a parcel of fluid from here to here, energy has to be conserved. So the fluid parcel will have gained gravitational potential energy. That energy had to come from somewhere. The two places it could come from are kinetic energy and thermal energy. We already saw in the previous video series that thermal energy is related to pressure, and that we could describe it as an energy density. And similarly, we developed an idea of a kinetic energy density. So it makes sense here. We can say the energy density here has to equal the energy density here. And that is indeed what Bernoulli's equation says, that as a statement of conservation of energy, the pressure at location 1 plus the kinetic energy density at location 1 plus the gravitational potential energy at location 1 has to equal the pressure at location 2 plus the kinetic energy density at location 2 plus the gravitational potential energy density at location 2. So the new bit we're adding here are these potential energy density terms. Remember, potential energy is just mgy. So if I divide by a volume, the mass divided by the volume would be the density. And so that's where the rho comes from. Now this does definitely look like a daunting equation. But it turns out that in a lot of practical problems, you'll get a lot of cancellations. Oftentimes, you may have the case where the two pressures are the same. That can happen if, say, things are exposed to air or something like that, in which case those might cancel. Or you may have it that the dimensions of the pipe don't change, so then the speeds will have to stay the same. There are lots of possibilities, and definitely with gravitational potential energy density, you're always free to set y equals 0 at the lowest bit to at least make one of these things go away. So again, to make for a more concrete example of this, let's say you have some sort of a pipe that looks like this. And so down here at location 1, let's say the fluid is moving at 2 meters per second, and we'll say it's water. Here at location 2, we'll say it's moving at 3 meters per second. And so this would be my height of location 2. Let's say that the height of this elbow is 10 meters. If I measure the pressure here to be 200 kilopascals, what I'd like to know is, what is the pressure here? Okay, so one of the things that we can do to make life a little easier on ourselves is we can say that this height y1 is equal to 0. So then that makes this height y2 here equal to 10 meters. By doing that, that at least makes the gravitational potential energy density term go away. So we can go ahead and start writing P2 plus 1/2 rho V2 squared plus rho GY2 equals P1 plus 1/2 rho V1 squared plus rho GY1. And here we can set Y1 equal to 0. Okay. So this is definitely one of these cases where it will be profitable to do things with letters in order to and be clever about grouping in order to minimize the number of substitutions you'll have to do in your calculation. That's probably where a lot of people will have challenges, is just in that last practical step. So let's keep it symbolic for now. So P2, we're going to subtract each of these terms from the left side to move it over to the right. So it'll be equal to P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared minus rho Y2. There you go. Now notice how these last three terms all have a rho in them. So we can clean this up a bit and say P2 is equal to P1 plus, we can pull a rho out from every single one of these terms. Now for these two terms here, they both have a half, so I can pull a half out and say V1 squared minus V2 squared, like that. And then minus, there I pulled the rho out, GY2. And by doing it like that, I won't have to substitute in rho 3 times. I'll only have to substitute it in once, and that will make life go a little easier for us. So let's go ahead and put in, we said the pressure at location 1 was 200 kilopascals, so we'll have to take that into pascals, so 200,000 pascals plus the density of water. So again, 1,000 kilograms per cubic meter. V1 we said was 2 meters per second squared minus 3 meters per second squared over 2 minus 9.8 newtons per kilogram times 10 meters. Okay. When you grind that all through, what you will get is a pressure of 99,500 pascals, or 99.5 kPa, in order to have consistent units with before. Okay. But perhaps it's worthwhile to do even one more example. So let's think about this. If you were to just take 2 pieces of paper, dangle them in each of your hands in front of your mouth, and blow, what do you suppose will happen to the 2 pieces of paper? Make a prediction on that, and maybe even want to try it before you get back with me. Okay, what you should have found is that the 2 pieces of paper wind up blowing together. So what's going on there? So it turns out that when I dangle 2 pieces of paper like so, let's try to draw it in some sort of semblance of 3D. There we go, something like that. Between here, we've got a speed of air that's not 0. And outside, say out over here, the speed of the air is 0. So we can make this our region 1, that our region 2. So we can go ahead and write down Bernoulli, P1 plus 1/2 rho V1 squared, so V1, V2 there, plus rho g y1 equals the same thing with 2's. All right, so whatever the height of the air is, it's the same inside and outside the paper. Those terms cancel. And the air is stationary in the middle. So if I solve for P1, I get that's P2 minus the kinetic energy density of the air flowing between the leaves. So the pressure of the air drops inside, and the two leaves wind up getting stuck together. Alrighty, and with that, I will catch you on the flip side as we start heading into thermodynamics.